12, 13, 14. Okay. Apparently some people are treating it as a Monday, Wednesday class on a Monday, Wednesday, Friday. So this is 13.6 in the text. There's also 1.7 in my notes. Okay. Now, this is something, directional derivative concept that's only makes sense in a multivariable setting. You wouldn't have something like this in one dimension because when you're dealing with y equals f of x, you want to know rate of change. How does y change as x changes? Since you only have one variable, you can only take the derivative along one direction as x increases, or if you really wanted to, you could find a rate of change as x decreases. So as x is increasing, your rate of change is dy dx. But if you want the rate of change as x decreases, it's not really interesting. That's just minus dy dx, really by the chain rule, because you're looking at rate of change with respect to minus x. So in the 1D case, you can only find a rate of change along one direction. Since moving along the real number line. Now, let's look at 2D. So just only one step up. Now, you know how to find the rate of change of a function of xy with respect to x. That's partial derivative with respect to x. And you know how to find a rate of change as y increases, so partial of f with respect to y. And you might be thinking, okay, in one dimension we only had one direction to work with. Here we have two, but really you have more than that. You actually have, as soon as you get to even two variables, you actually have infinitely many directions along which a function can change. Because what about rate of change as x and y change together in this direction, or this direction, or this direction, any direction? That's what directional derivatives are about. So if I take this direction and I label it by a vector u, how does f change as x and y change in such a way that you're moving along, so how they change in a direction of a vector u? Because you might have a situation where a function maybe isn't changing very much along this direction or this direction, but it could be changing a lot more along this direction. In fact, it's of interest to know in which direction of the infinitely many choices available does f change the fastest? Like, where's the direction of steepest increase or steepest decrease? Or along which directions does it not change at all? Is it a constant function? So this is why we have directional derivatives. Now, in order to define a directional derivative, we need something that I actually have already introduced, but I just want to review it. The gradient vector, bless you, which we've used a few times. So gradient of f is a vector that includes all the partial derivatives of your function with respect to whatever independent variables you have. So in most cases that we'll be talking about, you have df dx, df dy. And then if you're in 3 dimensions, partial with respect to z. All right, so we take all those first partial derivatives of a function that has only one output. So one output, many inputs. Okay. And we just gather all of those partial derivatives and we put them in a vector. Okay. Now, it turns out that there are certain differentiation rules that apply to gradients. They're very similar to the differentiation rules that you learned in Calculus 1, because, and it makes sense because what does the gradient consist of? It consists of partial derivatives. Dang it. But, and while you could just use the,
Bless you times 4.
times infinity, God. While you could just use the same old differentiation rules you learned in Calculus 1, apply to each partial derivative individually. Because I thought this is dust-free chalk, but I'm beginning to wonder. Although, actually, any chalk we have, we stock in the department, it says like anti-dust or dust-free or whatever. And at times like this, I'm skeptical. But I have used chalk that is explicitly not labeled dust-free, and that stuff is lethal. Okay, in fact, it should be banned. So, having these rules specifically for gradients lets you work with a vector all at once, and it can be a time saver. But you'll see that all these rules closely mirror differentiation rules that you're familiar with. So, for instance, a gradient of AF plus BG, where A and B are constants, and F and G are functions. That's just A times the gradient of F plus B times the gradient of G. So just as a derivative of a sum is a sum of derivatives, you can say the same thing about the gradient. Constants can always be pulled out, just like they can for derivatives. So all of that is no different. So we refer to this as linearity. When any operation follows rules like this. We also have product and quotient rule, just like for derivatives. So the gradient of a product, so you have F gradient of G plus G gradient of F. And you'll see that it also mirrors the product rule for ordinary derivatives. We also have the quotient rule. So those of you who remember the ordinary quotient rule for derivatives, what do you think the quotient rule should be for gradients? Give it a shot.
G gradient F minus F gradient G over G squared.
Yeah. Yeah, so it's exactly the same. You just, instead of saying derivative of, it's gradient of. Okay. And finally, we have, squeeze it in over here, the power rule. So the gradient of f raised to the nth power is just n f to the n minus 1 times the gradient of f. All right, so all of this works pretty much as you expect it to because we're just dealing with derivatives and you know how those work. Okay. Now, so with a gradient, I can define what a directional derivative is using another operation that I've mentioned now and then, as you learned from Calculus 3, a dot product. Now, you remember from Calculus 1, ordinary derivative is defined in terms of a limit. And I could define a directional derivative in the same way. In fact, I do that in the notes. But in the interest of time and relevance to homework problems, I'm just going to show you a formula for it. So first of all, I have to prescribe that U is a unit vector. So I don't know from Calculus 3, what do I mean by a unit vector? Yes, magnitude of 1. So I'm using the double bars here to refer to magnitude of a vector. Some calculus books use absolute value, which drives me crazy. Now, the definition of magnitude would be square root of the sum of squares. And by default, I'll just work with 3 dimensions, but of course this applies in however many dimensions you have. That magnitude must be equal to 1. And that's going to be very important because otherwise the definition doesn't work. Make sure it is a unit vector. Okay. Then, the directional derivative of a function f in the direction of u is just, oh, here's how we label it. We use a capital D, and then the vector u is uses a subscript of f. And a formula is actually now pretty simple. It's just a gradient of f dot product with u. And if I write out what the dot product is, so that means it would be partial of f with respect to x times u1, the first component of u, plus partial with respect to y times u2. And then if there's a third dimension, it would be partial with respect to z, u3, and so on, however many dimensions you have. And that's it. That's the directional derivative. All right. So, some special cases of interest. First, if u is a vector that has components as 1 and 0, I'm going to work in 2 dimensions here. What is this vector also called, especially in a physics setting?
Pi hat.
Yeah. All right. So in that case, we only care about the x component. So if you use this up here, or it could be like 1, 0, 0 in 3 dimensions, then the directional derivative is nothing more than partial with respect to x. So our partial derivatives we've been using, those are directional derivatives. It's just that those directions are the coordinate axes. Similarly, if u is this vector, 0, 1, which is called j hat, then the directional derivative, so we're just looking along the y-axis, so that's partial with respect to y. All right. So in the other case, we're changing x and y together, and we're seeing how f changes along that direction. Now, here's one formula for a dot product, and that's the formula we'll most often be using. I guess you could say it's the ones that mathematicians prefer. But there's another formula for the dot product, also is used most often in a physics setting. I don't remember what the other way to compute a dot product is.
AB cosine beta?
Yeah, where A and B are they're magnitudes of the vectors you're taking a dot product of. So it'd be the magnitude of the gradient vector times the magnitude of u, but we already know what that is. That's 1 by the definition. And then cosine theta, where theta is the angle between the two vectors. Okay. Now, this definition, we're not going to use it very often in practical applications, but it does help us define some important concepts. Because, as you all know, cosine theta can only assume values between what and what?
Cosine 0.
Minus 1 and 1. Okay. Now, let's look at 3 cases of interest. When cosine theta is equal to the maximum possible value of 1. So, what would theta be? Now, theta is going to be between 0 and pi, or 180 degrees. That's how we define the angle between vectors, because I'm using this angle, not that one. So, keeping this in mind, if cosine theta is equal to 1, what must theta be?
0.
Yeah, 0 degrees, or 0 radians. So, geometrically, how do the vectors relate if the angle between them is 0?
Yeah.
Same direction. Yeah, so they're sitting on top of each other. So this might be u and this might be gradient of f. So what's happening is, so in fact we can say that u, it has to be the gradient itself divided by its magnitude. And we can also say that the directional derivative is going to be magnitude times cosine theta, which is 1 in this case. So it's just the magnitude of the gradient vector. That's the largest value it can assume. Now, of course, this is a magnitude, so it's going to be positive. When a derivative is positive, a function is what? How's it behaving? It's increasing. So, we refer to u as the direction of steepest ascent. So, of all the infinitely many directions that we could choose, like in the xy plane or xyz space, this is a unique direction along which f is increasing the most rapidly. All right. Now, let's flip this around. Direction of steepest descent. So, in that case, we want cosine theta to equal minus 1. What would theta be in that case? Yeah, it's pi, or 180 degrees. So what's happening here is, well, how do the vectors relate this time?
They're opposite.
Opposite directions. To have an angle of 180 degrees between them. So this might be u, and this would be gradient of f. So we define u to be the negative of this case. So minus gradient of f over its magnitude. So the steepest possible descent you can get, or the most rapid decrease, is just the negative of this. So it's minus magnitude of the gradient. The direction of steepest descent is of considerable interest in applications because many methods for finding the minimum value of a function. Now, next section, next week, we'll talk about how to find maxes and mins, kind of like we did in Calculus 1. But for more difficult problems, where you're basically trying to search for a point at which a function has a minimum, the direction of steepest descent, so minus the gradient, is a way to go because it's a way to be guaranteed of making progress towards finding a smaller value. So in fact, there's a method called the method of steepest descent that's covered in upper level courses. So it's a numerical approximation method to find minimum of a function of several variables. Okay. All right. There's a whole field of mathematics called optimization. It's all about finding maxes and mins of functions of many variables. It's very important in business, for instance. And everything I'm talking about in this section, next section, plays a foundational role in that branch of math. Unfortunately, we hardly ever offer a class on it, but we do have one, or two actually. Okay, so here are the extremes: most rapid increase, most rapid decrease. Now, there's one other case of interest. So we've talked about cosine theta equal 1, cosine theta equal minus 1. Let's look at cosine theta is equal to 0. So what will be the angle in that case that makes that happen?
90.
Yeah, 90 degrees or pi over 2. Okay. So how do if you have two vectors that have an angle between them, the cosine is 0, how does that ever relate to each other in that case? They're perpendicular, also known as orthogonal. For the situation like this, so this is your u and this is your gradient of f. So gradient of f is perpendicular to u. So what happens in this case is the directional derivative is 0. So we can say that f is constant along this direction. In other words, it is following a level curve. At least in a two-dimensional case, especially. All right. So where the directional derivative is 0 is important because of the importance of level sets, or level curves, level surfaces, etc. Now, unlike the other two cases, there's no simple formula for u except in 2 dimensions. So looking at the two-dimensional case, so the gradient of f at a certain point x naught, I'm going to refer to it as components a, b, but that's just going to be partial of f with respect to x. Oh, sorry, I need a point 2d here. X naught, y naught. Okay. So partial with respect to x at that point, partial with respect to y at that point. Okay. So what would be the direction that would be perpendicular to a vector AB? So in 2 dimensions, it's particularly easy to get. So u would be, so to get a perpendicular vector in 2 dimensions, all you have to do is swap the components and then negate one of them, either one. So like b minus a. Because if you take the dot product of this with this, you can confirm you're going to get 0. But u has to be a unit vector, so you have to normalize it. And actually, I could do plus or minus of this vector. Either one would work, because it doesn't matter which component you negate, as long as you negate one of them. So what's happening is, at a certain point, at this point, x naught, y naught, say if the gradient is happens to be pointing in this direction. So this direction, then right here, is steepest ascent, most rapid increase. The opposite direction, that is steepest descent. And then the perpendicular directions, we have two of them. So this is the direction of whatever level curve is passing through that point. And the fact that a level curve or any kind of level set is always orthogonal to the gradient, that's going to help us later on when we define alternative equations for tangent planes or tangent lines. Okay. So now what I'll do, okay, so I have an example where we'll go through, you'll see all of this in use. Now, as you can expect, there's going to be a question on the first test about directional derivatives. And it's going to be something along the lines of maybe this example I'm going to do now, or something I'll include in the homework. And I have to say that of all the questions I would put on this first test, this one tends to be the most heartbreaking, because it should be among the easiest points you can get, because the other questions, most of them are definitely going to be harder. And a lot of students just mess up because they forget how to do a dot product or certain basics of vectors that you're supposed to know from Cal 3, which is why I'm reviewing them now. So don't let these relatively easy points slip away. Okay. All right, so our function, two variables, is x squared y plus y cubed. And I'm going to, and we'll be seeing what's happening at a particular point. X on y is 2 and minus 2. Okay, now, before we do anything related to directional derivatives, we need a gradient. So what is the gradient of this function? That's an x squared.
X squared plus 3y squared.
Yeah. Okay. X squared plus 3y squared. All right. And now we'll plug in our point. X of y on is 2 and minus 2. So that's going to give us minus 8. And then 6. Okay.
16.
Yeah. That's what's puzzling me. Okay. Because we have. Okay. Sorry. My brain was just like short circuiting. I was like, yeah, because that's also what it says in my notes, but okay. My brain was determined to go another way. I think what I did was I plugged 2 in here and I squared it twice. Okay, so that's a gradient vector at that particular point. Okay, now So if I want to take this annual directional derivative, like let's suppose I have u equal to, so I want the vector which x and y are changing together at the same rate. So it could be like vector 1, 1. However, I cannot use u equal to 1, 1. What's wrong with this vector for directional derivatives? What do I need to do to it?
Normalize or
Yeah, this vector as written is not normalized. So what do I need to divide by? What's the magnitude of this vector? Square root of 2. Yeah, because, so you're going to take a sum of squares of all the components and then take the square root. So that's 1 over square root of 2, 1 over square root of 2. So now I can take the directional derivative in this direction. So that's going to be this gradient, minus 8, 16.
revelation.
What?
Ignore that.
Okay, but does anyone else have a question? Okay, all right. Dot product with this vector, and that means multiplying corresponding components and adding them up. Actually, algebraically speaking, the easier thing to do would be set aside this 1 over square root of 2 for the time being and then put it back in at the end. Okay, and we're just going to get positive 8 over square root of 2. So along that direction, so 1, 1 is pointing this way at a 45-degree angle, f is actually at the point x is 2 and y is minus 2. So from this point, but going in this direction, we see an increase. Okay. All right. Although some of your K-12 teachers might say I'm writing this improperly. How's this supposed to be written? What? Yeah, because I can multiply by square root of 2 over itself, and then get, and after I simplify everything, then, yeah, 4 root 2. Okay. Of course, your teachers always told you, just as mine always told me, to never have a radical like square root of 2 in the denominator. Did anyone ever tell you why? Okay, I'll tell you why. As an example, okay, well, square root of 2 is roughly 1.414, 2135, etc. So if you want to compute the reciprocal of that, if you want, so that'd be 1 over square root of 2. But then if you were to rationalize that, it would be rewritten as what? If I rationalize this, like was done down here. Yeah, and that's how you're accustomed to seeing it, like in all your, when you're learning your angles for sine and cosine, it's always written that way. So now if you want to compute 1 over square root of 2, which is now written this way, and you want to perform the division, well, you're just dividing by 2. And if you had to carry it out by long division, it wouldn't be so bad. But written the other way, 1 over this, that kind of long division would be pretty unpleasant by comparison. And if you keep in mind that this convention of rationalizing was put in place a long time ago, before there was all the technology that you have today, when we actually had to carry out some arithmetic on paper by hand, that this convention was put into place. And we stuck to it. And I'll bet half the math teachers that make their students do this may not be aware of where it came from. And who knows, for all I know, some of you could be thinking to yourself, what's long division? Yeah, it's times have changed, but that's why. Well, like, people who worked with the very first computers know that it is more efficient for a computer to multiply by 0.5 than to divide by 2. And when computers are performing bazillions of operations per second, you might think, well, who cares about that now? But little things like that really do make a difference. Okay. So this is one direction I picked out randomly, and now we have the directional derivative, and we know it's increasing in this direction. So first, any questions about computing this directional derivative? It's this gradient dot product with u. Now in a problem, like in a homework or a test, again, make sure that u is a unit vector. Because a problem might say something like, find a derivative along this direction, it gives you some vector u, and it's not normalized. So don't forget to normalize it before you start. Okay. Now, what about direction of steepest? We'll just go descent. It's an application that's one's more interesting anyway. So that's going to be minus the gradient over its magnitude. So that would be negative of minus 816 over okay. So then, and this would be your u in this case, along which is going to be the most rapid decrease. So we're going to have 816 over 264, 320, square root of 320. Okay. Now, and actually, I can simplify this quite a bit because
Should we have negative still in the numerator?
here, yes. Sorry, I forgot to distribute the negative across all the way. Yeah. We good? Okay. All right. Okay. Because certainly the square root of 320 can be simplified quite a bit. Okay, so 20, 32, square root of 5. So I get for trying to do all this in my head. Okay, so now we can simplify this to 1 over square root of 5 minus 2 over square root of 5. Okay. All right. So this is the u along which f decreases most rapidly. Now to see how rapidly it decreases from that point, well, from before, the directional derivative is going to be minus the magnitude of the gradient. So that's going to be minus the magnitude of this vector right here, which is 8 square root of 5. Okay. So along that direction, that's the rate of decrease. In the opposite direction, it's going to be increasing that rapidly. All right. So any questions about steepest descent direction? All right, so this minus the gradient over its magnitude. Okay. And then, because we're in 2 dimensions, if we want the direction along which f remains constant at this point is perpendicular to this vector. So what we can do then is we can swap these two components and then you negate one of them. Well, right now we have opposite signs, so we're going to have the same sign. So u is going to be plus or minus 2 over square root of 5, 1 over square root of 5. Okay, so if you use this direction over, okay, in the formula for a directional derivative, so gradient dot u, in this case you're going to get 0. So, like I had over here, this situation, increasing, so the derivative is plus h square root of 5. This way it's minus h root 5. Along these directions, perpendicular at 0. So, questions about this example?
So what was this on the bottom right? That was our.
Here?
Yeah,
Okay, this is the level curve direction. So,
yeah.
yes. So if we take this steepest descent direction and find a vector perpendicular to it, that's where we get this one. So for purpose of your notes, swap, negate one of the components. Doesn't matter which one. In higher than 2 dimensions, it's not as easy to find a vector perpendicular to another one. If you have 2 vectors, you can find a vector, bless you, perpendicular to both of them. So you don't remember how you do that. What operation gives you that?
The cross product.
Cross product gives you a vector that's perpendicular to 2 other vectors, only in 3 dimensions. So in fact, you could say this is kind of like a scaled down to 2D version of a cross product. In fact, if I just tacked on a z component of 0, then this is exactly what would happen. So in general, if you have n-dimensional space, you have n minus 1 vectors, a cross product like operation gives you a vector that's orthogonal to all the other n minus 1. And cross product we're certainly going to be using from time to time in this class, just not yet. Okay, I'm basically out of time, but so we're going to continue with this section on Monday anyway.
I have a question. It's not like you. Is that given